Okay, so I don't know if this will help. Let me sort of talk about limits and continuity in a kind of, I'm going to sort of, no, I'm not going to do it. Okay. Okay, so this chapter is about continuity, right? And can anybody tell me, anybody remember what continuity is? How do we describe continuity, right? So, you know, in the old, you know,
For every neighborhood of
right, for a function to be continuous, for the function to be continuous at p, what does that mean? Like here's f of p. Anybody have some sense of what continuity is?
yeah, for every neighborhood of F
Yep.
or the output of P,
Yep.
there's a neighborhood of P including P that map to that entire neighborhood.
Yes, exactly, right? So the definition is that, right, so f is continuous at p means, that, right, for all neighborhoods of f of p, and we usually use an epsilon, for all neighborhoods of f of p, there exists a corresponding delta neighborhood of p such that f of the delta neighborhood is contained inside of the epsilon neighborhood. Okay, so for every, right, so for every epsilon, right, every epsilon neighborhood of p, there's a delta, every epsilon neighborhood of f of p, there's a delta neighborhood of p that gets mapped inside there. Okay, so that all the points inside this, inside this neighborhood are within epsilon, that get mapped to within epsilon of f of p. Okay, so the picture is like this, right? You know, one picture is like this. Suppose if I took my epsilon like this, suppose I take epsilon like this. So f of p plus epsilon, f of p minus epsilon, right? And you notice that if, so what's my delta gonna look like? What delta, what if I took a delta like this? Would that work? No, right? I need to take, in this case, you know, my function is changing pretty rapidly. I need to take actually a delta about this, like about this wide, right? Do you guys see that? That if I take the delta like this, then everybody in this delta neighborhood stays within, you know, the prescribed epsilon neighborhood, right? If I took a different epsilon, if I took this as my, you know, this as my epsilon, so let's say f of p minus epsilon prime, f of p plus epsilon prime, right? So I change my epsilon. You see that I could, you know, I could take a delta, you know, I could take a pretty big delta, right? Like this. If I took a delta like that, you see that everything in that delta neighborhood, you know, all those values stay inside my epsilon neighborhood, right? You guys see that, right? So being continuous at a point means that you know, whatever epsilon you're given, you can find a corresponding delta around p so that the guys in the delta neighborhood get mapped into the epsilon neighborhood. Okay, and you can do that for any epsilon you choose. So if I choose, you know, if I choose this epsilon, right, I say you've got to stay between here and here. Well, I can, you know, there's a delta that works, right? There's a delta that works. I can, you know, choose some tiny delta, and everybody stays inside. If I say I'd like you to stay between here and, you know, I'd like you to stay this close to f of p, well, there's a delta that works, okay? And the ability to do that is called continuity, okay? If you can do that, that means that the function is continuous there, okay? So, right, so, you know, in the metric space world, we don't think in terms of graphs. Rather, we take the graph and sort of rip it apart into, you know, here's p and here's f of p, right? Where, you know, this is one metric space and then this is another metric space, right? and you say, I have a neighborhood, continuity means that no matter what neighborhood I take around f of p, there's a neighborhood around p that gets mapped inside there, right? But that's exactly the same thing as this picture on the graph, right? No matter what neighborhood of f of p I choose, there's a neighborhood of p that gets mapped in, whose values get mapped inside there. Okay, so I hope that makes things a little clearer if it wasn't clear before. Okay, so that's what we're talking about. And what we said last time was that we're going to give this sort of alternate characterization of continuity. Right. So that's following theorem that a function, yeah. So you have a function from x to y. So this is continuity. I forgot to say it. So this is continuity at a point. Continuity on a set means that you're continuous at every point, right? Maybe I don't need to say that, right? So like this function here, you see that, if I took a different p, it's going to be continuous at that p, right? This function is continuous, on this domain here, right? But notice one thing that will be important later. The delta changes. The delta changes depending on the point, right? So like if I take this point and I take an epsilon like this, right? Then my delta is this one here, right? If I take this point and I take an epsilon, I take the same epsilon, well, my delta is actually quite big. I can take a much bigger delta here, right? Because the function is flatter here, so it doesn't vary that much, right? So the delta, right? This delta depends on the point, right? It also, of course, it also depends on the epsilon, right? When you change the epsilon, the delta changes. But also true that for this function, the delta depends on the point. Yeah, and
when we're talking about these deltas, are we talking about like delta is the maximum radius, or just any of
any?
them? Okay.
Yeah, delta is any. Yeah. So all you need is that there exists a delta neighborhood, right? Yeah, and it's true. I could have chosen a smaller delta, and that delta would have worked here. Yeah, good point. Okay, back to the alternate characterization of continuity. So you have a function from x to y, and f is, so the theorem is that f is continuous on x if and only if for all open sets, what notation did I use, V? For all open sets V in Y, the pre-image of V is open in X. Okay, so when you pull an open set back through the function, the thing you get is still an open set. Okay, so you've got these two metric spaces, right? You've got a function going from one to the other, and we're saying that continuity is actually the same thing as this business of whenever you have an open set here, you pull it back, you get an open, whatever, so the inverse image is also going to be open. Okay. Okay, so those two, that turns out to be equivalent to this definition here. Okay, so which way should we do first? Okay, let's do this one first. Okay, so suppose f is continuous on x. Okay, suppose f is continuous on x. That means that you're continuous at every single point, right? And so you know that, given any point, right? So f continuous on x is the same thing as saying that at every point, x in x. You have the continuity property, right, for all neighborhoods of f of x. There exists a neighborhood of x such that the image is contained in the epsilon neighborhood. Right? That's what continuity means. Right? Given any point, you can play this find the neighborhood that gets mapped inside the other neighborhood game. Okay. So we want to show that. So let V be open in Y. Okay. Let V be an open set in Y. We want to show that F inverse V is open in X. Okay. We want to show that F inverse V is open in X. So we have this V over here. We take the pre-image. We've got F inverse V over here. So we want to show that, given any point here, right? Given any point here, we can find a neighborhood around it, right? That's contained in F inverse V, right? We want to find, so, i.e. that given any x in F inverse V, there exists a neighborhood n around x such that n of x is contained in F inverse V. Right? How do we know that such a neighborhood exists? Anybody able to say it?
It's an open set.
What's an open set?
Like it has all the interior points. Like all its points are interior points.
What's all interior points?
Interior points guarantee there's neighborhood that contains all elements of. Sorry.
So we're trying to show that x is an interior point. How do we know that x is an interior point? Right?
Yeah. You have to find that neighborhood, like by definition, that all the elements in that neighborhood are also elements in the matrix space.
Yeah, in this inverse set.
Yeah.
Yeah.
Usually.
Okay, so let's think, right? What do we know? We know that what do we know? We know that V is open, right? We know that V is open. So we have this point here. We have some point here, right? And we know that V is open, right? We don't have that F inverse V is open. What we do have is that V is open, right? Okay. So if we look at F of X over here, what can we say about F of X over here? And
Well, f of x is interior.
F of X is interior, right? So well, F of X is interior to V, right? Because V is open, right? So what does that tell you? So we know there's a neighborhood over here, right? So there exists some neighborhood around F of X that's contained inside of V, right? That's what interior means. There's some neighborhood around it that's contained in V, right? Okay, so what do we want? What are we trying to get? We're trying to get a neighborhood around X so that that neighborhood is contained in the pre-image of V, right? That's the same thing as saying that f of n of x, f of the neighborhood, is contained in V. Can you find a neighborhood around X whose image is contained in V? Yes. Yes, you can, right? Why? And go ahead.
Because it's continuous, so we
Because it's
have the
continuous.
delta neighborhood.
Exactly, because of continuity, right? Right, continuity means that given any neighborhood over here, we can find a neighborhood here that gets mapped inside it, right? Well, that's the one we're looking for, right? That's exactly what continuity is, right? So, V is open, so f of x is interior. That means that we can find a neighborhood around here. F is continuous, so we can find a neighborhood around x that gets mapped inside there. But that's exactly what we wanted. We want a neighborhood that's mapped inside there, right? So by continuity of f, we know that there exists a delta neighborhood around x such that f of the delta neighborhood is contained inside of that epsilon neighborhood, right? Which isn't contained inside of V, right? So this neighborhood, i.e. this delta neighborhood of x, is contained in f inverse of V, right? F of the neighborhood is in V, the neighborhood is in f inverse of V, or the preimage of V. It's not really proper to say f inverse because this function might not be invertible. I should say preimage. Okay, so that's one direction. Do people get that? People get that? Right? Anybody get that? Anybody confused by that? Feel free to say so. Right. So, right. We're trying to show that continuity implies that you've got this pullback of open sets are still open, right? We say, okay, start off with an open set and pull it back. Pull it back. We want to show that guy's open, right? So take some point inside of it. We want to show that that point's interior. We want to show that point's interior. Well, let's map it forward. Map it forward. We know that this thing is open, so we can find a, right? So this point is interior, so we can find a ball around it that's contained inside of V. But then by continuity, we know that there's a ball around here that gets mapped inside there, right? And so this guy, so that shows us that x is interior to f inverse of x. Okay. Okay. Let's go back. Let's go the other direction now. Okay. So going backwards, right? Suppose we have this open sets property, that the pullback of open sets is always open. We want to show that f is continuous at every single point, right? So we know that no matter what open set we take over here, the pullback of it is still gonna be open, right? And we want to show that, we want to show that if we look at a pair of points, then whenever we take an epsilon ball around here, we can find a delta ball around here that gets mapped inside it. Okay, right? So we know. Assume that for all open V and Y, the preimage of V is open X. We want to show that given any point X in X, that given any epsilon neighborhood of f of x, there exists a delta ball around x such that f of the delta ball is contained in the epsilon ball of the image. Okay. Okay. Did anybody see how that might work? Here's our y, here's our x. Right? We have this sort of pullback of open sets power, right? Pullback an open set, it's still going to be an open set. Okay, that's what we have. what we want is that if we have a point here, and we look at this thing, and we look at the epsilon neighborhood here, we can find a ball around X that gets mapped inside the epsilon neighborhood. Can we find that? How do we find such a ball?
I think just take the inverse.
What?
I think just take the inverse.
Just take the inverse. So you say, well, look, let's take the epsilon. You've got this epsilon ball. Take the inverse of the epsilon ball, right? That'll give you something containing X. And what do you know about it? You know that this inverse image is open, right? This thing is open. So X is interior, right? So what? So you know
Each ball is also E.
there's a ball around it, right? There's a neighborhood around it. Well, that's your delta ball. The end. Okay. So so you say, well, look, given the epsilon ball, which is open, you know that the pre-image of the epsilon ball is also open and contains X. So X is interior. So X is interior to it. One, two, three. Right, X is interior to it. So there exists a neighborhood around it that's contained in the set. Right? There's a neighborhood around X that's contained in this open set. Right? But then F of that thing lies inside the epsilon neighborhood. Right? Because this thing lies in the pre-image of that. So F of it lies in that. Right? And that's what we wanted, right? That's continuity, right? We started off with an epsilon neighborhood, we found a delta neighborhood that was mapped inside it. Okay, done. Right, so F is continuous at X. Right? And X was arbitrary, so we've got continuity everywhere. Okay. How are you guys doing? You always look down to me. Are you down? You don't look good. You're okay. I don't know. Maybe it's just my view of reality. Okay. So there's a corollary to this, which is pretty straightforward, which says that if that continuity, you could also replace this with closed sets, right? If for all closed sets, F inverse is closed, that's the same. That turns out to be the same thing. And the proof of that corollary just relies on the fact that F inverse of a set complement is the same thing as F inverse of the complement of that set. Right. So, right, if you can show that this is true for all open sets, this fact will give it that you're true for all closed sets, and vice versa. Okay. So this is a pretty simple fact. You can prove this. Okay. So there's a corollary. Same sort of statement is true for closed sets. Okay. Okay. So okay. So I think I'm not going to talk about the continuity of vectored valued functions. I'll let you read that. Basically, the main thing is saying that if you have a function, if you have a vector valued function, it has these component functions. Right. A vector value function, consists of component functions. And basically, continuity of the vector valued function is equivalent to continuity of each of the component functions. So I'll let you read that, I think. If I have extra time, I'll do it. But I think I want to get to the more important stuff. Okay. Okay. So, okay. So here we get to the really interesting stuff. Continuity and compactness. Continuity and compactness. So the first thing is we'll give a definition. Yeah, okay. So you have a function going from a set into Euclidean space. Okay. And if there exists some real number such that all the values of f are smaller than that real number, okay, then we say f is a bounded function. Okay, f is a bounded function. Okay, so this is pretty simple idea. It just means that you don't head off towards infinity, right? That your outputs are contained in some range, right? It means that your outputs are contained in some neighborhood of the origin. Okay. Okay. So the first theorem we're going to talk about is the following: that if you have a function going from one metric space to another, and it's continuous, so if f is continuous and x is compact, then the image of f is also compact. Okay. Yeah. Okay. So a continuous image of a compact set is still going to be compact. So that's pretty nice. Okay, so the proof of this is as follows, right? We want to show that f of x, the image, is compact, right? So what does that mean, right? What does compactness mean? It means that we've got this open cover goes to finite subcover property, right? Right. So in other words, we want to show that given any open cover G alpha of f of x, it has a finite subcover of f of x. Right? You can find some finite subcollection that still covers the set. Okay. Okay. Anybody see what we're going to do? Anybody have the idea? Here, right? We've got a compact metric space mapping into some other metric space, right? And so it gets mapped over here, right, to some f of x, right? And we want to show that f of x is still compact. Okay, so we start off with some open cover here, right? We start off with some open cover, right? There's a bunch of open sets that cover this thing, right? And we want to show that we can take a finite subcover of them, right? So, right, the pieces are, right, we've got compactness of x, right? We've got a continuous function, right? So what are we going to do? Write down something. Everybody write down something. What are we going to do? Okay, turn to somebody nearby and say, here's what I think we're gonna do. Turn to somebody nearby.
This is discontinuous. This will be covered.
So I was just thinking
Is it verse continuous?
because
Because when we say
why
that open
is
cover one, not
finite
X,
subcover?
we can go take
Sorry,
finite
every has a
subcover.
finite
That,
subcover.
and then bring it back, yeah.
Each of the other is like we take any cover of ice and map out into y. Then because the cover is the basic space ice, like cover
And this
the
was the
body
one that was
ice.
like fixed.
Julia, why don't you talk to somebody, I don't know, front or back?
Cover the
Okay.
body ice. And because that cover in ice has a finite.
Yeah, you can just say hi.
But yeah, that must be each size. That's usually subcover. Yeah, because it's continuous. Yeah, that's fine.
Okay,
Yeah,
okay, anybody wanna say what they're, anybody wanna say what they're thinking? So, right, we're trying to show that this thing, we're trying to show that this thing is compact. We take an open cover of it, right? We know that this guy is compact, right? We know that this thing is continuous. We just said that continuity has something to do with open sets. So what are we gonna do? I heard some people saying the right things. Go ahead, Anna.
We would take the open cover and map it back onto
Yeah,
X.
just
and
pull
take
it
the
back.
finite.
Exactly. Yeah. Pull the open cover back, you get an open cover, right? Because of continuity, you get an open cover of this thing. By compactness, you get a finite cover, and then just take the ones that correspond to it, and that will cover those guys will cover f of x. Exactly. Right? So you say, well, look, f continuous, so that tells you that f inverse of each of the g alphas is open, right? Because they're open, right? And when you pull back an open set, you still get an open set, right? So what do we get? The union of these guys is an open cover of x, right? It's an open cover of x, but x is compact. Right? X is compact, and so that gives you that there exists some finite subcover, G alpha 1, G alpha n, say, that covers X, right? But then G alpha 1 union G alpha n covers f of x, right? Because x is contained in here. X is contained in here, so when you map it forward, these guys are going to cover x's image, right? And so we've got a finite subcover, right? That's our finite subcover. Okay, so we have compactness. Okay, so just yeah, the picture. Keep the picture in mind. The proof kind of follows from the picture. Okay. Any questions? Any questions about that? Yes, Juan.
I just don't know how big boundness can help related to that.
Boundedness is not related to this.
Yeah,
sorry,
but-
sorry.
yeah.
It's related to what I'm about to say.
Okay.
Okay. So what I'm about to say is that, thus, corollary if you have a function going from some metric space into Rk, if f is continuous and x compact, then f must be bounded. Okay, right? So, right, if you have a continuous function on a compact set going into Euclidean space, well, you know that compactness means closed and bounded, right? So, I mean, really what we know is closed and bounded, right? So the image is compact, and so you know that the function, you know that the image is bounded, which means that the function is bounded. I'm sorry, I shouldn't say closed and bounded. That doesn't make sense for us in terms of a function. The image of the function is closed and bounded. The function is bounded. Okay, so that's a corollary, and that gives us that gives us one thing that I've been promising since the first day, the extreme value theorem. Okay, so the extreme value theorem of calculus, which says that if you have a function going from a compact set, a closed and bounded set, into R, if f is continuous and x compact, then you know that there exists some point P in X such that f of P is the supremum of f on X. And you know that there's a point Q in X such where f attains its infimum. Okay, so this is that thing from, calculus, which said if you're on a closed and bounded set and your function is continuous, right? The extreme value theorem says if you're on a closed and bounded interval and your function's continuous, then you attain your maximum, and you attain your minimum. Okay, that's what the extreme value theorem says. And that's what this is saying in a slightly more general context. Here we're saying if you've got a function on a compact metric space, we wouldn't have said this back in calculus, right? I have a function on a compact metric space. Closed and bounded interval, right, in calculus. But for us, you got a function on a compact metric space, you're guaranteed that the function will attain its supremum, and it will attain its infimum. Okay. In other words, it has a max, and it has a min. Yeah.
It has a global max, right?
Yeah, that's what this is saying.
Global min, yeah.
That's what this is saying. That
It's on the sub-
you reach your global max, you reach your global min. Yeah. Yeah. Okay. So the proof is, you say, well, we just said that the image is compact, right? Right. So we know that f of x is compact. Right? We know f is compact, and we know that the supremum of f of x is in the limit points of f of x. Right? The supremum is, the supremum is in the closure. Sorry, let me say this way. The supremum is in the closure of f of x. Right? It's either in f of x itself, or it's in, it's a limit point of f of x. Right? Right. But f of x is compact, which means it's closed, right? F of x is closed, so this is just f of x, right? So the supremum actually is an element of f of x. In other words, you attain it, right? Right. It's you know, it's some value. It's f of some value. Right. So so basically like this. F is compact, which means that f of x is closed and bounded. Right. By boundedness, you know that there is a supremum, right? So I should be a bit more careful. Bounded means that supremum of f of x and the infimum exist, right? By the least upper bound property, right? Right. Because we're in R, and we know that it's bounded, so it has the least upper bound and also has the greatest lower bound, right? We also know that the supremum and the infimum both lie in the closure of the set, right? But the closure, the set is closed, so the closure of the set is the set itself, right? Which tells you that supremum of f of x actually equals f of some point. And similarly for the infimum. Okay, so that's the extreme value theorem. Okay. Okay, the proof is simple after several weeks of work. Right. So it took, you see what it took to get to this point, right? We had to talk about compactness. We have to talk about continuity, et cetera, et cetera. Okay, everybody all right? Everybody all right? Okay, good. Okay, so, okay. Let me do just one last theorem, and this is kind of an odd one. I mean, I've seen it used a couple of times, but maybe it's just not something that I see used often. But, so here's the theorem. You have a function going from one metric space to another. Okay. And f is a bijection. That is, it's one-to-one and onto. Okay. So you have a bijection from x to y. Okay. And you have and x is compact. Okay. So let me write this. If x is compact and f is continuous, then the inverse function, right? It's a bijection, so now we have a bona fide inverse function. Okay, so the inverse function is also continuous. Okay, so you have a bijective map on a compact set. If it's continuous, its inverse is going to be continuous. Okay, so okay, so the proof goes like this. You say, well, we want to show that this guy is continuous. I'm sorry, we want to show that the inverse map is continuous. That means that the inverse of the inverse map is going to take open sets to open sets, right? So it suffices to show that for all sets V that are open in X, that f of V is still open. Right? It's because this is the pullback through the inverse of the inverse. Right? So you're pulling this function backwards through this function, right? So you're going forwards through f, right? Okay. So consider the complement, V complement. Okay. It's closed. It's closed in X, right? Well, it's closed in X, and X is compact. So what do we know about the set? You've got a closed set sitting inside a compact set. Anybody remember? Closed set inside a compact set. The closed set is going to be compact, right? So VC is compact, right? Okay. Now that tells you that, and F was continuous, so F of V of C, F of V complement is also compact, right? So we've got this compact set sitting inside of Y, but being compact means that it's closed. Okay. So what does that tell you? Well, F of V complement is the same thing as F of V complement, since F is a bijection. Right. Since F is a bijection, I think this is a homework problem. Anyway, since F is a bijection, you know, the complement of the image is the image of the complement. Okay. So what does that tell you? That tells you that F of V, right? That tells you that F of V is closed, is open. Right? This thing is closed, but this thing is the complement of F of V. Well, so the complement is closed, so this thing is open. Right? And so we've done what we wanted. Right? We've shown that given any open set, F of V is going to be open. Okay? And so the inverse is continuous. Okay, next time we're going to start off with the main result about continuity, which is something called uniform continuity. And this has to do with what I was alluding to earlier about how the delta changes depending on the point. Okay, right? If you got some function, right, you know, the delta, you know, depending on your function, that's not even a function. If you have some function, right, the delta depends on the point. But for some functions, the delta doesn't depend on the point, right? Like here, if I take an epsilon, yeah, I would take some value, and then I take, you know, plus epsilon minus epsilon. You know, you can see that I can choose the delta uniformly throughout my space here. It doesn't depend on the point. That's called uniform continuity, and what we're going to see is that continuity on a compact set guarantees uniform continuity. Okay, which is a cool fact, cool and useful fact. Okay, that's it for today.